Hi there, my name is Figa and welcome to MV Tutors. If you would like to book a session after this, make sure to visit our website on www.mvtutors.co.za and make a booking there. Alternatively, you can comment on this video and just ask for one. Right, so today we'll be talking about rates of reaction calculation. Now, that's the calculation of the equilibrium constant. Now, I like to start my sessions with a vision. And what's that vision? It's a past exam paper. Now, this is a question from a past exam. Let's just look at the question. 6.4 here says calculate the equilibrium constant for the reaction that's given there, and we are given the information above. So if you, after reading this question in its entirety, feel like you cannot answer this question or you don't understand it, then stick around. Let's get some principles in order to be able to answer this question, and then at the end we're actually going to answer this question. So let's start by defining the equilibrium constant. It's denoted by Kc, and it is actually equals to the concentration. So this box bracket represents concentration of the products. Okay, and on the exponent there you put the number of moles. Okay, number of moles. Okay, and it's divided by the concentration of the reactants. Okay, also as an exponent you're gonna put the number of moles. Okay, right, so that's the definition. Let's take a typical example for this. So let's say you have 2a plus 3b, and then it's reversible, and then you have 4c plus 5d. Now, to get the equilibrium constant of this, remember we said concentration of products over concentration of reactants. So let's start with the products. Now, if you can notice here, let's change the color. These are the products over here. Okay, so that's what we start with on top. So we have C, concentration of C, all right, and number of moles, it's got 4 moles, so that comes on top there. And you multiply it with the concentration of D. Okay, and number of moles is an exponent divided by concentration of A, 2 times D, not dB, sorry, and it's got 3 number of moles. Okay, so that's one principle that we need in order to be able to answer the question. Okay, another principle that we'll need is what I call the Rice method. Okay, it's RICE. Okay, I can also put another E, but this E is okay, let's define the whole thing. So the R stands for ratio. Okay, and typically if we look up here, the ratio is 2, it's the number of moles. Okay, the number of moles. And then the I stands for initial. So this is the initial number of moles that each one of these starts with. Typically it'd be given in a question, or they might ask you to solve it. And then C stands for change. So it's the change in moles as well. Okay, so E stands for equilibrium. Okay, so it's the equilibrium of the number of moles. So that's the rise that I'm talking about. This one is in moles. Okay, the change is also in moles. Okay, and then the equilibrium is also in moles. Now that last E is also standing for equilibrium. Okay, but the unit is different. This equilibrium is actually the concentration, which is in mole dm minus 3. Okay, decimeters, moles per decimeters. Okay, so that's it. One more principle which you need to learn is how to calculate this mole. Okay, so let me change the color of the pen. Let's use green. So number of mole is denoted by N is equals to M, which represents mass, over a capital letter M, which represents molar mass. Okay, now where do we get a molar mass from? We get it from the periodic table. Now, these are all the principles that we need to answer the question. So let's go ahead and put these principles into practice. Okay, so let's read the question. It says initially 0.16 mole of H2. Where's H2? Let's find it. Where is it? Okay, it's nowhere here. Oh, there it is, down there. And excess S, which is in solid state. Where is it? There it is. Are sealed in a 2 decimeter cubed container, and the system is allowed to reach equilibrium at 90 degrees Celsius. An exact amount of PbNO. Okay, where's this one here? Okay, it's in this equation right there. Solution is now added to the container so that all the H2S gas, where is the H2S? Okay, there it is. We also have it in this equation here. Present in the container at equilibrium is converted to PbS. Where is that? Oh, it's in this equation only. According to the following balanced equation. Okay, that's the balanced equation. The mass of the PbS precipitate is 2.39 grams. Calculates the equilibrium constant Kc for the reaction. All right, so we need to be able to use what we have been given in order to solve what needs solving. So let's start here. What are we given? We are given an initial amount, so we can use that in the RICE method under initial. Okay, we're given 2 decimeter cube. We can use that on that last equilibrium E for concentration, so we'll divide the moles by it. Okay, we're also given the mass of PbS precipitate. Okay, what can we do with the mass? We can calculate the molar mass. That is why I have a periodic table over here so that we can calculate our molar mass easily. Now, why do we need the number of moles? It's so that we can calculate our concentration successfully. Let's see. Okay, so we can calculate number of moles of this PbS. Where is PbS? It's over there. Okay, now we can see that if we cut, this has 1 mole, that has 2, that's 1 over there as well. Okay, so we can calculate the number of moles here, and we are going to use those moles to also represent this H2S. Okay, and this is the equation that which we are calculating from. So we have H2S there. Its number of moles will be equals to that number of moles and that number of moles. Now there's one more thing I need you to know about the equilibrium constant. When we are calculating the equilibrium constant, we do not consider solids. We only consider gases and aqueous solutions. So S will not be in our equation. All right, let's get down into it. Let's get into the nice, delicious calculations. So, like I said, first of all, we need number of moles. Okay, with the information we've been given, we need a mass and we need a molar mass. Okay, so in terms of mass, we are given 2.39. Molar mass, we should calculate molar mass of PBS. Okay, so this is for, let me just put it there, PBS. Okay, PB, so we go to our periodic table, we look for PB, there it is there, it's 207, plus for S, we go look for S. Where is S? Can you see S? Right over there. It's 32. Okay. Now we're going to bring in our calculator. Just bring in our calculator right there. Let me just add these at the bottom. Let me rewrite this. So I need 207 plus 32. Yeah, that gives me 239. Okay, and then from there I can say 2.39 divided by 239, and that gives me 0.01. okay, mole. All right, so there we go. We've got our number of moles. Now we can go back to our equation and say this one, H2, the number of moles is 1:1:1, which means all of them have that. Now let's set up our table, our rice table, so that we can put these into perspective. So rice, we'll start with rice, which is ratio. Okay, maybe let's use a different color pen just to distinguish everything. Okay, so we'll have the R, which is in moles. Okay, and then we also want the I, which is in mole as well. And then the C, remember, it represents change, which is also in mole. And then we want the E. The first one is in mole, but the second one is in mole divided by decimeter cubed. So because we're dividing, it should be -3. Right, and then what are our reactants? Let's put our reactants. Come back to this equation. The reactant is H2, so we'll put H2 up here. And then the product is H2S. So we'll put H2S over here. Okay, now let's just go on and draw our table. Because I don't have a graph paper, I have to do it manually, but in the exam, surely you'll have a graph paper. Okay, so let's just complete it right over there. Good, let's do this one. Hold on. This is wasting precious time we could be using to calculate, but let's get it done real quick and then we'll get into the calculation. There we go. One more. Okay, let's just leave it there for now. Okay, let's change the color so that we know what we are doing. Right, now let's go back to the ratio. Okay, so the ratio is 1:1. Okay, 1 mole is to 1 mole. All right, and that's coming from the equation. Okay, and then the initial number of moles. Okay, maybe this one I should put moles with an S, and then this one will be just mole, the rest, because we're talking about the SI units there. The initially we are told that initially there it is, 16 mole of H2. Is it 16 or 0.16? 0.16. So we'll put 0.16. That's the number of moles. Now when it comes to products, what I normally like to do is that to separate the products from the reactants, I put a double line. Okay, just to show there's a separation, because sometimes you might get 2 this side and 2 that side. It happens, but in this question we have 1, so that's cool. Now normally with products you always start with 0 number of moles of products, and then there's a change, and then there's an equilibrium one. Now this, what we just solved, this 0.01 is actually the number of moles in equilibrium. Okay, or we can put it under change, it's the change. But for the purposes of understanding this question, let's put it under equilibrium. So we solve under equilibrium, it's 0.01 mole. Okay, now what happens here is that, what is the change? Usually, well, all the time, the change here is that we add something to get the equilibrium one, and here we need to subtract the change. Okay, so here the change that we added, in order to get 0.01, we added 0.01. Okay, now the reason we need a ratio is because there is a relationship between the ratio and the change. Okay, so since it's 1:1, that means the change is also 0.01, and it's based on the ratio. If the ratio was 2:1, for example, or 1:2, then if we had 2 on H2 side, on the reactant side, then we'd need to double that and have 0.02. But because it's 1:1, it's exactly the same. Okay, that's the relationship. That's why we need the ratio, because it helps us put the change into perspective. Okay, so now you see I have a negative sign there. I need to subtract 0.01 from 0.16, and then we'll get the answer is 0.15. Okay, now we have a number of moles at equilibrium. Now we just need to divide them by 0 by I'll show you now. 0.15 divided by, we were given here in the question, they told us it's 2. Okay, 2 dm cubed. So we'll divide that by 2. This side will do the same. It's going to be 0.02 0.01 divided by 2. Okay, so bring up your calculator. Okay, let's put this in a calculator. It's 0.15 divided by 2, and we get 0.075. The next one, we have 0.01 divided by 2, and then we get that's equals to 0.005. Okay, thank you so much, calculator. So what we're going to do now is that we have everything we need to calculate the equilibrium constant. And remember, so we're going to say equilibrium constant is going to be equals to the concentration of the products, which is H2S, and there's no exponent. Exponent is 1 divided by that of the reactant, and it's also 1. So concentration here is for H2S is 0.005 divided by 0.075. Let's put that in the calculator and see what we get. Is our final answer. So it's 0.005 divided by 0.075, and our final answer is 0.067. Let's stop there. Now there are no units for a constant because they both cancel each other. Okay, I hope you understood. If there's anything you missed and you didn't understand, well, you know what to do. You can book a session with me. Thank you.